So here we're going to take a look at our second type of indeterminate form that is not 0 over 0 or infinity over infinity. So for our second example, we have infinity minus infinity, and what we'll see is that these limit problems are two fractions that are subtracted or added in some cases. And so what we need to do is keep in mind that every single one of these L'Hopital rule problems where you have an indeterminate form that is not 0 over 0 or infinity over infinity, we're going to try to force back into that form. So in order to have two fractions go back to 0 over 0 or infinity over infinity, we're going to have to rewrite it as a single fraction by finding a common denominator. So if we take the limit as x approaches 1 of 1 over ln of x minus 1 over x minus 1, we're going to have a very good idea of what the ln of x function looks like. So over on the right, I'm going to refresh your memory on that. Remember, ln of x is the inverse of the exponential function e to the x. So for every coordinate point that you know of that y equals e to the x goes through, its inverse is ln of x. So you would switch the xy coordinates and plot. So the main feature is the x-intercept is 1, 0. You've got a vertical asymptote at the y-axis, and as x goes to infinity, y goes to infinity. So it's going to be really important that we understand what this graph looks like, and I'm also going to label this vertical asymptote so you remember that. So as x approaches 0 from the right, it's going to negative infinity. Now, when I plug 1 in, I'm going to take this part a little bit slower than I would if we're thinking of this quickly, but if I plug 1 into the first fraction here, ln of 1 is 0. So remembering back to what does it mean when I get 1 over 0? And I know algebra-wise we think of it as undefined, but as a limit we're getting or approaching 0 is the idea. So if I have 1 over 1 millionth and I change that fraction, multiply by a million, I get that that's close to infinity. So as x goes to 1, we approach infinity. So really this is infinity, and we get the same results by plugging 1 into the second fraction. So once we get this indeterminate form and we see we have two fractions, we're going to go ahead and rewrite that so that it's a single fraction. And we do so by common denominator, which is the product of x minus 1 and ln of x. And the left fraction looks like it's missing x minus 1. The right fraction ln of x, so minus ln of x, we bring the minus sign upwards. If we plug in 1, go ahead and plug in 1 into the top, we get 1 minus 1 is 0, minus another 0 is 0, so the top is 0. If we do the same at the bottom, we also get over 0. 1 minus 0, ln of 0, or ln of 1 is 0. So after that, if we finally get it to now one of the original indeterminate forms, we're going to go ahead and apply L'Hopital's rule, which is the derivative of the top separately from the bottom. So that's important to keep in mind because we have people forgetting that it's the derivative separately on top and bottom. Okay, so the derivative of the top is 1 minus negative, or the derivative of a constant is just 0, minus 1 over x all over, and now we do the product rule. Okay, so x minus 1, the derivative of x minus 1 is 1, keeping ln of x the same, plus, and then this time we keep x minus 1 the same, times the derivative of ln of x, which is 1 over x. And so at this point we can simplify this a little bit. Okay, we're going to take a look at what fractions we have, and I always encourage you guys with L'Hopital's rule, that's probably the #1 mistake I see, is right after taking the derivative, not simplifying, and then starting to do the plug-in again. So in red here, I'm going to write the word simplify first before you guys apply L'Hopital's rule again. Okay, so simplify, and that means what can you do algebraically to simplify the fraction? And you can't have fractions within a fraction, so what you're going to do is get rid of that. So what we can do is multiply the top and bottom by x to get rid of the x. Okay, so x to 1, you're going to get x. So limit as x approaches 1. So the top just distribute. So when you do, you get x minus 1 on top. On the bottom, you really have two terms here. This ln of x is one term, and then this is another term. So when you distribute x to ln of x, that's easy. X to this is going to cancel out the 1 over x at the tail end of that expression. So we've got x ln of x plus x minus 1. Now at this point, when it looks nice and simplified there, we're going to plug in. And so when we do, we get 1 plugged into the top is 0. And then when we plug the 1 in at the bottom, we get this here is 0, because ln of 1 is 0, plus 0 again, that is 0 over 0. So since we have a second indeterminate form, we apply L'Hopital's rule again. So limit as x approaches 1. The derivative of the top now no longer will be 0, right? So if we take the derivative of the top, we got 1. The bottom, x ln of x, we do have to apply a product rule there. So derivative of x is 1 times ln of x plus, keep x the same, the derivative of ln of x is 1 over x. And then the derivative of x minus 1 is just 1. And so do our plug-in again. Ln of x, when we plug that in, is just 0. This is 1, and this is 1. So our final answer is 1/2. And in parentheses up above here, I'm going to make a note. This is apply L'Hopital's again.